Now that we have finished the backend of image compression, the symbol coding that we do with Huffman coding in the example I presented, let's go to the front end of image compression. Basically, what we are going to describe in this video is this part. So let's just start with this component. What we have is an image. And the first thing that a JPEG does or a lossy transform compression does is divides the image into blocks. Each one of these blocks has n by n pixels. And we're going to give examples of what's the value of n, but just to give you an idea, JPEG uses 8 by 8. So basically JPEG codes almost independently every 8 by 8 block of the image. These are non-overlapping blocks, so here are 8, then 8, then 8, then 8, okay? And we go all the way, and there are techniques what to do if your image width is not a multiple of 8 and so on. So don't worry about that for the moment, those are just technical details. So we take an n by n block, and we're going to encode each one of those n by 8 by 8 blocks. And as I say, they're encoded almost independently. Now, this is what you do with one image, but this is if you only have a black and white image. What happens if I have an RGB image? So JPEG is what's called colorblind. JPEG doesn't know how to deal with color, the standard itself, but there are some assumptions that are made. Originally, what you could do is you just take the red. Remember, every channel is a two-dimensional array of pixels. So the red looks like this. You divide the red in 8 by 8 blocks and you encode the red. You do the same with the green, you do the same with the blue. And that's perfectly legitimate. Now, normally there is basically a lot of correlation between the channels. So what basically JPEG does, instead of coding RGB, it goes into what's called YCBCR. I'm going to tell you in a second how to do that. But these are, instead of 3 channels RGB, it has 3 channels which are Y, CB, and CR. This is a luminance channel, which is basically what you will see if you have a black and white TV or a black and white monitor. You will get a color image, but you will only see basically the black and white component, the luminance component of it. And these are the colors. Okay? And this is a very simple transform. This is actually done by a 3 by 3 matrix. So you basically are going to have your Y, CB, CR as a column. You have a 3 by 3 matrix here, 3 by 3, and you have your RGB values. So the Y is a linear combination of the RGB, the CBR is a linear combination, the CB a linear combination, and the CR another. And this matrix is invertible. So once you decode the YCBCR, you multiply by the inverse of this matrix and you get back the RGB. So the very first thing that JPEG does, it takes your color image, multiplies it by a matrix. So basically every pixel, let's say 100, 150, 200, you multiply by the coefficients here. This is a constant matrix that is given, is very well known. It appears all over. If you just Google YCBCR, you're going to get the values of this matrix. So it goes over every single pixel of the image and transforms it from red, green, blue arrays into YCBCR arrays. Once again, two-dimensional arrays where every pixel, now instead of being an RGB, is a YCBCR. So it has those, and then it's going to encode each one of these arrays independently. So let's look at Y. It will go into Y, and it will divide it in 8 by 8 blocks. Okay? And that's all what's going to do. And then it's going to take each one of these 8 by 8 blocks, and it's gonna encode them, as I say, almost independently. But for the sake of this presentation, we're gonna consider them independently. So it's gonna encode a lot of 8 by 8 small images. And how it's gonna do that? It's gonna do that with a discrete cosine transform, a transform, then a quantization, and then a symbol encoding, as we have seen so many times with the diagram of JPEG. So now we have an 8 by 8 block, and all what we need to think about now is that we have a small 8 by 8 image.